Hello, let's say the intro asks you to print all the paths in a binary tree. So what are all the paths in this tree? We have one path, 0, 1 and 3. 0, 1, 3 makes one path. Why is it the path? Why not anything else after this? Because there is no more node after 3. So basically the left and right children of 3 are none. So that makes it a complete path, and that's when we print it. So this is also going to be our terminating condition, that if we have met a node that has no children, then that should constitute a whole path, and we should print it immediately. So let's write the pseudocode. All paths. What this will take is we will have a node and we are going to use a stack. Then we check if the node is equal to none, then we immediately return. If not, then we are going to append it to the stack. Stack.append node. Then we check if node's left child is equal to none and node dot right child is also none, then that means we have reached a leaf node, and that constitutes a whole path in the stack by now. So what we do is we just print the stack. Once we have printed, we need to now pop the last element in the stack, because then we want to check if there is anything on the right side so we can add it to the stack and then print it. So we do stack.pop and then we return. After this is done, we will write a recursive call to all paths with nodes left child and the stack. And then after this, we will have all paths node right child with the stack. And after the two recursive calls, we need to pop once more from the stack. I'll show you later why we need the second pop. So let's run this test case against our code and see how it is working. So I'm going to keep track of what is in the stack, and I'm also going to keep track of what is printed, and I'm also going to keep track of the recursive calls. So first time, the all paths function is called with the node 0. I'm just going to write the node, not the stack, in here for the sake of simplicity. So when we are here, we append to the stack, 0 is added to the stack. This condition is not true. So all paths recursively calls on 0's left, which is 1. So all paths is called with 1. Here we are here, we check is it none? No. We append it to the stack. So 1 is added to the stack. This condition is not true. Then all paths is again recursively called with 1's left, which is 3. So we call all paths with 3. We are here, we check, no, this is not true. We append 3 to the stack. Then we check if the left and right of 3 are none. Yes, they are none. So at this point, we print 1, 0, 1, and 3. So let's keep track of the printed ones here. So this path is now printed. We print it, then we pop from the stack. So this is gone, and we return back. So this call is done, which was the left call of 1. Then the right call of 1 will be made, which is AP with 4. Call with 4, we are here. No, this is not true. So 4 is appended here now in the stack. Then we check this condition is true for 4 because it has no children. Then we immediately print stack, so which is 1, 0, 1, and 4 are printed. This path is now printed. Then we pop from the stack, and then we return. So when we return, that means AP4 is done, 3 is done. So both left and right of 1 are done. Then we pop the last element of the stack, which is 1. Why we popped it here, if you see, because both left and right are done, and so we pop this, because then we need to go one level up. So this is popped. then we are here. So when this was popped, we were only done on the left side of the all paths call with 1, which was the left side of 0. Then we need to call the right side of 0, which is all paths of 2. When we are on the 2, this is the call we just made. We are here, this condition is not true, so now 2 is added to the stack. Then this condition is not true for 2. We call 2's left. 2's left is 5, AP 5, 5 is called. We are here, 5 is appended to the stack. This condition is true for 5, so we print the current stack, which is 0 to 5 is printed. Then we pop the last element of the stack and we return. When we return, that means AP5 is done, the left call is done. We have to call the right side now. AP right side is 6. When we are at the 6, this condition is not true. 6 is appended to the stack. We check this condition is now true for 6. Then we print the whole stack as is, which is 0, 2, and 6. When that is printed, the right side is also done. And then we pop again. So when we pop, 2 is popped again. And then again, this is returned. So if you see, all the 4 paths are now printed using this recursive approach. Thank you.